If you look at the syllabus, we were supposed to be beginning chapter 7 on Monday. That's okay, because we're going to do chapters 7 and 8 all together, and we're going to catch up a little bit. I think we'll spend today on chapter 6 and then move on to chapter 7 next time. Go ahead.
Oh, sorry to interrupt you. Will exam 2, that's going to be through chapter 8 or?
So what happened last time I taught the class, apparently I need to learn not to be so optimistic in how fast I get things done. Last time we ended up giving a test at the regular time, but only part of like chapters 7 and 8 was on it. And so I'll make that clear as we get closer to it. Yeah? Will we be talking about optical activity at all? I thought about this, and the answer is no. I think it's simple enough that you can probably get it from the study guide and the practice exam. I'm happy to answer questions on it, but I don't think it's probably worth too much of our time in class. It's sort of, there is a little bit of math, it's sort of dividing, but the idea is that chiral molecules rotate plane polarized light, and that you can tell something about the ratio of one enantiomer to another in a mixture based on what optical activity is. So take a look at that. I think it'll be valuable to you. I think it's possible that it shows up on a future standardized exam. I don't know whether MCAT or DAT still do that, but you may want to know at least a little bit about it. Be able to do the problem in the practice exam that's on that subject, but other than that, I think we just won't go there. Yeah?
So not on your midterm?
Possibly on the midterm, but it'll be easy. Yeah. Okay. So, chapter 6 is all about why reactions happen and how they happen. Did I press record? Yeah, we're good. And why reactions happen is an issue of thermodynamics. And how reactions happen is an issue of kinetics. And you may have heard about either of those things. Thermodynamics basically refer to the question, in a given process, do you go downhill in energy or uphill in energy? And in chemistry and physics, downhill versus uphill in energy is defined by this term delta G, or the change in Gibbs free energy, which is related to the equilibrium constant for a process via an equation you already know. By the way, I told you before that a difference of about 1.36 kilocalories per mole at room temperature is worth a factor of 10 in equilibrium constant. So you're really not going to be doing natural logs, so don't worry about memorizing anything there. Clearly, a negative number in delta G leads to a large positive value in equilibrium constant. Now, another way you can think about free energy changes for a process is having two basic components. One is called enthalpy and the other is called entropy. And these can be somewhat difficult concepts to understand, though for organic chemistry they're relatively simple. For a process, enthalpy, a change in enthalpy means basically are the bonds you form stronger than the bonds you broke? So in a chemical reaction. So enthalpy is basically going to be, we're going to consider it as an issue of bond strength, or the bonds formed stronger than the bonds that you broke. This can apply not only to bonds, but also to non-covalent interactions. We won't talk about that, but when you get to biochemistry, you'll talk about binding constants of various enzymes to their substrates, and the change in enthalpy for those kinds of situations is related to the non-covalent interactions you form when an enzyme binds its substrate versus the non-covalent interactions that you lose. Delta S is entropy, and that's also somewhat difficult to visualize or understand. You've been taught that it represents disorder, and basically there's just, it comes down at the molecular level to a basic issue of probability. There's a whole lot more ways to be disorganized than there are ways to be organized. So for example, if you come up to my office and you see my Lego Millennium Falcon that's sitting on my desk, my pride and joy, it's all the pieces are organized, and there's only one way for them to be organized. And there's this book that's like 150 pages long with instructions on how to organize all those pieces to make the Millennium Falcon. There's only one way to do that. Now, there were gazillions of ways to have all of those pieces mixed together in various combinations. So probability is that more often than not, the Lego Millennium Falcon is going to be found in pieces mixed together rather than in its one state. This is why I brought it here to my office instead of leaving it at home where children can touch it, right? People ask me, when you built that, did you build it with your kids? And I was like, no. I don't trust them to touch the Legos. A missed father opportunity, I'm sure, but at least the Millennium Falcon's intact. So in general, for organic reactions, we're going to pretend like entropy doesn't exist because changes in entropy are usually small. There are situations, though, where a change in entropy might be important, not in a way that you need to predict or use on an exam, but in a way that may be worth thinking about. For example, if you have two starting materials and they come together to make one product, that might lead to a negative change in entropy, which is going to be unfavorable for free energy. Another situation would be if you have one product, one starting material going to two products, particularly if one of those products is a gas like CO2, the entropy increase for a process would be very large, and that can help move a process forward. Another case that, again, you're not going to necessarily need to reason through this, but we'll talk about it occasionally as we deal with reactions. If you have some molecule that has two reactive portions in the same molecule and you make, a ring, when you connect two parts of the same molecule together, you reduce the amount of conformational flexibility the molecule has. And if you don't believe that, just consider the conformations available to hexane versus cyclohexane, right? Cyclohexane, you've got two chair conformations. Regular hexane, you've got tons of different conformations about each of those carbon-carbon bonds. So for a cyclization process where you make a ring of some kind, often entropy change can be negative because you're decreasing the order of the system. In my lab, we use this cyclization to prepay some of the entropy costs for a protein folding, as an example. And that's probably all I'll have a chance to say about that in this class. If you want to know more, come talk to me because I think it's really cool. But speaking of things I think are cool, Amber was happy enough that I was willing to give HiFit a try, that she decided that it might be fun to do something that I like that she doesn't like. So we watched episode 1 of The Mandalorian last night. And, I've seen that many times, but she was like, I gotta say, it just, it's not that great. Like, okay, fine, your loss. She doesn't like violence, and I think that's probably a good decision. But it's Star Wars. Okay, so the thing that I will ask you to sort of reason through that we need a good feel for is enthalpy changes in a reaction. And as I said, this is an issue of bonds formed versus bonds broken. So let's first talk about how we talk about bond strength in organic chemistry. In some ways, this relates to the idea, right, that two orbitals mixed together, in our hydrogen system, you had the 1s orbital here, 1s orbital here, you had a sigma bonding orbital here, a sigma anti-bonding orbital, a sigma star. The electrons in hydrogen are able to go down to the sigma orbital lower in energy, And this energy difference is basically the bond strength. That's how much energy it takes to promote an electron back to the original atomic orbital. But you can visualize that in a number of different ways. For example, you may have seen in general chemistry some kind of plot like this, where this is sort of 0 in energy, and we're showing distance here between two hydrogen atoms, HA and HB, and at infinite distance the energy is 0. As they get closer together we get to some minimum, and then as they get closer than that they start to repel each other. Again, bond strength is the energy it's required to get back up out of this minimum and go to infinite distance. But the way organic chemists talk about bond strength is related to the following process. So for hydrogen, we're going to represent breaking the bond, making the electrons go back here, or getting out of this energy well and going back here. We're going to represent that with the following mechanistic step. These are different arrows than you've seen before. They are fishhook arrows. The pointy part of the arrow only has one side, and that's to indicate that that arrow means only one electron. If an arrow's like this, that's 2 electrons. An arrow's like this, that's 1 electron. So you should get used to that. The process that I'm showing you is called homolytic bond cleaving, because each of the 2 atoms involved in the bond get an electron. And for hydrogen, the change in enthalpy upon doing that is plus 105 kilocalories per mole. And some people will call this the bond dissociation enthalpy, which means how much energy you have to put in to break the bond. Notice that bond dissociation enthalpies are always positive. It always takes energy to break bonds. Now, some of you are thinking, hold on, we were told in high school / in our childhood that releasing bonds, or breaking bonds releases energy. And if they told you that, they were oversimplifying. Breaking bonds always requires energy. The energy that's released is when the bonds that you make after you break the bonds are more stable than the bonds you broke. That was just about as confusing as the whole pKa and pH business. So let me give you some examples of how to consider whether a process overall is favorable. And as I said, we're going to mostly ignore entropy. And so as we think about changes in bond strength, we're going to use that as a way to determine whether we think a process is favorable or not. So let me illustrate for you a substitution reaction, wherein we have this lovely tert-butyl chloride and water, and we're wondering sort of what the equilibrium constant is, and we make tert-butyl alcohol and HCl. We want to know overall, is this process favorable versus unfavorable? One way we can do this is to keep track of the bonds that we break in this process versus the bonds that we form. So we're going to break a carbon chloride bond, and we're going to break an oxygen hydrogen bond. And then we're going to make this oxygen carbon bond and make a hydrogen chlorine bond. So I'm going to keep track of the bonds that I broke, and I will look up the bond dissociation enthalpies for the following processes. That is breaking of the carbon chlorine bond to get a carbon with 1 electron and then a chlorine with 1 electron. And the bond dissociation enthalpy for this process is plus 331 kilojoules per mole. Organic chemists prefer kilocalories per mole because that's what we've always done, and we don't like to, I don't know, we're stubborn. I will use kilojoules per mole sometimes when I'm too lazy to calculate kilocalories per mole, and I just looked up the numbers from the text. So does it matter? Do you have to be able to convert between these two? No. A good rule of thumb is kilocalorie per mole is about 4 kilojoules per mole. All right, so that's uphill in energy to break that bond. Then for the hydrogen-oxygen bond, breaking in a similar way, that's uphill by 498 kilojoules per mole. So overall, breaking those bonds should give you, require you to put in about 829 kilojoules per mole. But that's only part of the picture, right? Because we're also forming bonds. So now we have to consider the strength of the bonds formed, but we got a problem because all of the bond strengths or bond dissociation enthalpies we're going to look up are for the bond breaking process, and we want bond formation. But fortunately, it's very easy to do. You just flip the equation and take the opposite of the bond dissociation enthalpy. Here's what I mean by that. For the bonds that we form, we're going to envision going from the dissociated situation to having the new bond. If it was going this way, backwards, delta G would have been plus 401 delta H would have been plus 401 kilocalories per mole. Because we're going backwards to make the bond, it is now minus 401 kilojoules per mole. Maybe let me just illustrate what I'm trying to say. Don't write this down, but I'm afraid I'm not explaining it that well in words. So what I'm saying is that the process of breaking the carbon-oxygen bond would be uphill by 400 kilojoules per mole. If you want to know how much downhill making the bond is, you just flip the equation and take the opposite. Does that make sense? Okay. Right, so that's the carbon-oxygen bond. Let's do the hydrogen-chlorine bond. Again, if you start with hydrogen and chlorine separated, and then you make the HCl bond, delta H is going to be minus 431 kilojoules per mole. So overall, for the bonds that we form, we're going downhill in energy by minus 832 kilojoules per mole. All right, so now we can simply add all of these together. You will find if you add all of these chemical equations together, all of the species with a single electron end up canceling themselves out. And because, this is something you don't want to know, but I gotta say it, because enthalpy is a state function, it doesn't depend on process, it doesn't depend on how you got there, it just depends on starting point and ending point. So it's totally fine to calculate the overall change in enthalpy for this reaction by adding together individual bond dissociation types of reactions. In any case, what we observe overall, excuse me, I'll clear my throat, is bonds broken is uphill by 829 kilojoules per mole. Bonds formed is downhill by 832 kilojoules per mole. If we can subtract, that's like minus 4, or something like that. Oh, 3. Yeah, I can't subtract. I told you this. Ask me which my right hand is. I only know that now because I'm writing with it. Downhill in energy by about 3 kilojoules per mole. At that is a small number. That's fairly close to 0. And so if we wanted to, we could calculate what the equilibrium constant is. All I'm going to do is say the equilibrium constant is somewhere between 1 and 10. So this, how favorable is this reaction? Not much. It's about, it's somewhere between 1 to 1 versus 1 to 10, maybe favoring products a little bit over starting materials. Overall, your book will tell you that the way you calculate bond strength is to take the bond dissociation enthalpies of the bonds you break and subtract the bond dissociation enthalpies of the bonds that you form. That's a totally fine way to do it, and that's what we've done here, only I just incorporated the subtraction when we flipped the direction of these equations. Yeah?
Would this reaction still happen in water because the Cl wouldn't really bond, it would still be separate?
Would this reaction happen in water? Because you're right, this isn't the whole picture. We haven't really accounted for concentration of anything here, and we also haven't accounted for the fact that yes, when you make HCl, you're going to get H3O plus and Cl minus, and that's a different thing too. So yeah, you do have to keep in mind that the actual situation can be altered. One of the most useful ideas that we will encounter is just the Le Chatelier principle, that if you either remove a product or add an excess of a starting material, you can push the reaction in a desired direction. Okay, good. Other questions? Yes.
Will we ever work with something where both electrons go to one?
Will we ever work with something where both electrons go to one? Well, see, that's a great question, and that's an issue of mechanism, which is how the reaction happens, but thermodynamics don't care about that. So it's just that we have tabulated all of these values. Now, I will tell you that the actual mechanism of this reaction, what actually happens, is not that the bonds break that way. It's that first, you don't want to know this, but this is in chapter 7, so maybe you do. Yeah. Where the chloride picks up with its electrons and leaves a carbocation behind. So yes, the chloro takes 2 electrons. And then, in the second step, water acts as a nucleophile, HOMO attacks LUMO, and you end up with this. And then, technically what happens if we are in water, Cl is over here, water is a better base than Cl, and so water will remove that proton and you'll end up with the product, and with H3O plus and Cl minus as you guys predicted. So that's sort of how it's thought actually happens. But again, thermodynamics don't care about pathway. Think of it this way. Whether or not you take the elevator or go up the stairs, your difference in potential energy on the 4th floor of the Benson building versus the 1st floor is exactly the same. Thermodynamics does not care how you got to where you get to. All right? I'm sure there's a religious application there. Something about perfection in Christ and the atonement making us whole, and then it doesn't matter how we got there, I guess. I don't know. Should have worked that one out a little bit. Should have beta tested that. Okay. So other questions? Yeah.
So it's a difference of -3 kilojoules per mole, and you said that the kilocalories per mole is about 4 times that?
Yeah.
So if that's at -12 and at 1.3...
No, I'm sorry, it's the other way. It's the other way. Yeah, so 1 kcal per mole is 4 kilojoules.
Okay.
So yeah, you're looking at a difference. It's less than 1.3 kilocalories per mole. That's less than a factor of 10. So you're going to favor products by more than 1 to 1, by less than 10 to 1. Yeah. By the way, this rule of thumb is just one that organic chemists know. It's not one I'm going to ask you about, but it can give you some context to understand what bond strengths and enthalpy changes in reactions mean. All right. So I want to clear up that misconception about breaking bonds releases energy with an example from biology. And I do this because when I was in 6th grade, I had to come up with some kind of writing project, and my dad, who was, by the time we all graduated, my mom said he had earned a couple of additional high school diplomas. had this idea that I should make up a rap related to energy and the conversion of glucose into energy. And now that I actually know about that process, there was some inaccuracies in that energy rap. It was sort of modeled after this is so embarrassing. It was so sort of modeled after the quote Mormon rap that came out in the mid-'80s, and anyway, I'm kind of ashamed. But now I know the actual chemistry, so we're going to talk about it. No, not going to happen. Hey, everybody, now listen to me. This is how your body gets energy. Woo! All right, yeah. We'll let you just imagine the rest. All right, so this is the first reaction of glycolysis, wherein ATP and glucose come together with the enzyme hexokinase to make glucose 6-phosphate. And you've heard of ATP as the carrier of energy. And so we're going to actually draw its structure. Let me just add the disclaimer at this point. Some of you are asking, do I need to memorize the structure of ATP? Please do not. I mean, if you want to, that's great, but as you know, you're not going to be drawing any structures in terms of answers on my exams. I suppose I could do which of the following is ATP, but we've got bigger things to learn.
Is ATP always with a normal ribose?
Is ATP always with a normal ribose? Yes, if it were deoxy ATP, you would be missing the 2' hydroxyl. Yeah. All right, so that's ATP, and the product of the reaction is, we're running out of space. Here's glucose again. That's an ugly chair. I'm afraid, is it gonna vanish like it did last time? No, all right. So I'm going to save myself time by copying and pasting. I know that irritates those of you that are working with pen and paper. So the reaction transfers a phosphate group to glucose. This is now glucose 6-phosphate. Do you have to memorize that structure? No, you do not. And ADP, copy, paste, where you've lost this last phosphate group. And I'll point out that even though ATP has this, large number of negative charges here, usually magnesium is the counter ion for ATP, and it's sort of chelated by those negatively charged oxygens, so that sort of takes care of some of the charge balance issues. We don't need to worry about that, but in case you were, excuse me, that's embarrassing. In case you were worried about the charge there, the magnesium counter ion sort of takes care of it. So let's look at what's changing here and what were the bonds that we broke. So here is the phosphate group that gets transferred. Still no. Is that the highlighter? Yeah, there we go, that's good. And the bond that gets broken is this one. And I will just tell you, it may not be apparent at this stage, this kind of bond, just so emotional. Oh boy. Phosphoanhydride bond. And it's relatively weak. And we will talk, and you will learn throughout 351 and 352 how to recognize weak bonds. You can just accept it as a given for now. The bond that we make down here is called a phosphoester bond, and it's a little bit stronger than the bond that we broke. Phosphoester versus phosphoanhydride. And you don't need to worry about those functional groups, but just accept what I've told you. If you could measure that bond strength via bond dissociation enthalpy as we've done before, the phosphoanhydride bond is weak, whereas, that's many arrows. It's kind of obnoxious. The phosphoester bond is stronger. And you can look up at various places, Wikipedia and so on. People have estimated what the free energy change is for this reaction in the cell. It depends on the conditions in the cell and what the concentrations of the starting materials and products are. But overall, this reaction is estimated to be downhill by 7.8 kilojoules per mole, which is large biologically. Multiply that by 4, you're in close to the 80s. I told you 1.36 is a factor of 10, an equilibrium constant, so this reaction is way downhill. And this is the first committed step of glycolysis. It's regulated because once you put the phosphate group on the glucose, you're not going back. And so you'll learn a lot about this in biochemistry, but this idea that breaking a bond releases energy isn't really true. It's breaking a weaker bond and replacing it with a stronger bond that releases energy. But understand that this free energy change, the energy that's released when this process happens, is basically lost as heat. I mean, that's why our body temperature is 37 C. The energy for doing additional processes comes from what we can do to the functional groups near the phosphate group and so on. You'll learn more about that in 352. Muscle movement, for example, involves transfer of phosphate groups that cause rearrangement in actin versus myosin, and that's pretty much all I know about that, so we just won't say anymore. Questions about that idea? Are you convinced that breaking bonds does not release energy? Go ahead.
So, if in kilojoules to kilocalories, do you multiply by 4?
Yeah, 4, dang it. Divide. Yes, 1 kilocalorie is 4 kilojoules. Sorry, divide by 4, we're about 4 kcals per mole. But even then, we're looking at a factor of about 100 in equilibrium constant. Thank you for keeping me honest with the numbers. We should just memorize the number in kilojoules and then we wouldn't have to do this. Yes?
So with other mechanisms in the biological system, does ATP always do this phosphoanhydride to phosphodiester phosphate, or
often what ATP does. The question is does it often resemble this? And the answer is yes. A lot of times it does. Sometimes you'll have some other functional group that actually will attack this phosphorus and this one will leave, but it's the same kind of process. And that phosphate transfer really is what drives a lot of biology. And you can get a sense for why that might be, right? You take a neutral molecule and now you got a couple of charges on it, and that can be something that an enzyme holds on to, and that can also influence other reactions. All right. This, by the way, is the investment phase of glycolysis. You've probably heard, well, hey, we're going to generate ATP in metabolism. Yeah, we are, but you got to prime the pump a little bit, and we're going to consume a couple molecules of ATP before we recoup our investment and get a few other molecules of ATP out of the process. Stay tuned. You'll get that in 352, and it's really fun. But okay, other questions? Yeah.
What exactly do you want us to know from this besides just that making bonds is more favorable?
Yeah, it's a lot of time we just spent just to know that making bonds is more favorable than breaking bonds.
Okay.
Yeah. If I give you a table of bond strengths, I could ask you to predict whether a process is favorable or not. You should have some practice problems in the study guide that should help you do that. It's worth doing that a couple of times so you know how to go through that. All right, I want to talk about reaction kinetics now. This is the issue of how. And kinetics matter. I told you thermodynamics don't care about kinetics, but kinetics is all about how reactions happen and how fast. And how fast a reaction happens is really important. For example, we are made of a lot of carbon and hydrogen, among other things. If you've ever, and we live in an oxygen atmosphere, and it would be thermodynamically favorable for all of the carbon in us to be oxidized to CO2, turning us into, I don't know, a bubbly pile of goo or something like that. But the reason that isn't happening is because that reaction is slow. Fortunately, the human combustion reaction is slow. So the issue of how fast a reaction happens is actually critical. And the whole reason we have enzymes is to accelerate reactions. Enzymes do not change whether a reaction is favorable or not. They just make it faster. And there's a ton that we could talk about there, but I want to focus in on organic chemistry. And we're going to talk about this with some examples. So I'm going to show you a reaction that comes from chapter 7. And we're going to talk about its mechanism. This is a substitution reaction because we replace this group on methyl iodide with this group. Cn minus is cyanide. It's got this Lewis structure, if you want to know. Let's see, I will tell you that the equilibrium constant for this reaction is much greater than 1. It's favorable, meaning that free energy change is negative for the reaction. And we could maybe estimate this a little bit from bond strengths, though whenever you have charges involved, remember all the bond strengths we have are for neutral type reactions, so where there's charges involved that can change things sometimes. We'll call these starting materials. Mostly because I don't like the word reactants. Starting materials takes longer, but I don't know why we do that. And we'll call these products. Just to give you an idea of what might be going on, I'm going to tell you that Cn minus is a nucleophile and that methyl iodide is an electrophile. I'll also say that iodide, after we break that carbon iodo bond, we're going to call this a leaving group because it left. Imagine that. So if you pay attention to what is going on, what we're doing is we're breaking the carbon iodide sigma bond. Breaking the carbon iodide sigma bond, and we're making the carbon-carbon sigma bond. All right, so let's think about some mechanistic hypotheses as to how this reaction might be happening. And this is where your HOMO and LUMO intuition is going to be very useful. So I'm going to present a few different hypotheses. We're going to talk about experiments that you might do to illustrate or to demonstrate which of these hypotheses is likely going on. So hypothesis 1. Let's say we make the carbon-carbon bond first, then we break the carbon iodide sigma bond second. If we did that, what we might predict was going on would be something like this. We'll have CN minus attack the carbon. We're going to draw an arrow that represents making the carbon-carbon bond. When you draw mechanisms, the arrow represents making or breaking the bonds that you're talking about. So the arrow that you draw is really tightly connected to what the products are. And we would propose some kind of intermediate. And let's say in this intermediate, we just made the new carbon CN bond, but we haven't broken the carbon iodide bond yet. I'm imagining that we'd have some sort of trigonal bipyramidal type structure. Carbon would have a negative formal charge here. It's okay if that's giving you heartburn. Why might it be giving one heartburn? Too many bonds to carbon. Yeah, that is what we call a Texas carbon. Because even though everything is bigger in Texas, carbon is not, and it still can't have 5 bonds, even in Texas. I don't actually know where that term came from, but every organic chemist knows what a Texas carbon is. We can think about a transition state that would precede the intermediate. A transition state is an energy maximum. And in this case, the transition state might look something like this. The bond between carbon and carbon would not have formed completely yet. So there would be a partial negative on that carbon, on the CN carbon as it's coming in to make a bond. We will represent transition states sometimes with brackets and the double dagger to indicate that, that this is a transition state. Starting materials and intermediates are energy minima, and so you can isolate them and observe them. Transition states you generally cannot isolate or observe. You have to infer them from experiments you do and from calculations you perform. All right, so this is step 1. We made the new bond, and then step 2, we're going to break the old bond. And then that would give us our leaving group and our new product. And the transition state for this step 2, I'm going to use TS to represent the transition state, would look almost like the mirror of the transition state 1. That is, the carbon-carbon bond is formed and the carbon iodide bond is lengthening and breaking. All right? So we would be proposing, like I said, an intermediate, 10 electrons around carbon, 5 bonds to carbon, and that's problematic. But molecules don't know anything about the rules that we make for them. And so before we understood this rule, this might have been a reasonable hypothesis. The mechanism that we've proposed here is what we'll call a stepwise mechanism, because all of the bond breaking and bond forming doesn't happen at the same time. If we drew an energy diagram for this process, what we might see is something like this. You have starting materials, you have a higher energy intermediate. We think it's higher in energy because the carbon's negatively charged. The transition state leads from the starting material to the intermediate. So this would be the transition state. Energy's on the y-axis here. On the x-axis is something that we might just call a generic reaction progress. And then there would be transition state 2 here, and maybe we get something, as I said, the products are lower in energy than the starting material, so you expect this to be downhill. So maybe we'll do that. This is transition state 2. Exporting to PDF doesn't like it when I have things bridging the pages, so we'll just do that. All right, I'm not saying that's how it goes. In fact, this hypothesis is wrong, but at least we're thinking about it sensibly. A mechanistic hypothesis accounts for transition states, intermediates, which bonds are breaking at which time. Questions about how we did that? Okay. Let's do another one. Mechanistic hypothesis number 2. Let's say we break the carbon iodide bond first, and then we make the carbon-carbon bond second. This is another stepwise reaction mechanism, only this time, instead of having Cn minus come in and make a new bond, we're going to break the carbon iodide bond. And that would get us, if we watch, that's going to get us to an intermediate in which a carbon is positively charged. That carbon is going to be trigonal planar. You should sort of be thinking about what the LUMO would be on that sp2 hybridized carbon. What is it? Empty p orbital, good. Iodide here was our leaving group. The transition state presumably would look like something like this, where the carbon iodide bond is just lengthening. Some people ask, well, how could this even happen? And understand that bonds are like springs, extending to a little bit longer length, going to a little bit shorter length. You can think of a bond as a spring sort of rattling around the bottom of this energy diagram, and if you give the molecule enough kinetic energy, sometimes the spring will snap. And so we'd be proposing that the iodide bond would break in some transition state. And then in a second step, we'd be proposing that the nucleophile, non-bonding lone pairs on the carbon, the HOMO of the nucleophile attacks the LUMO of our cation here. This is our carbocationic intermediate. And then we get our new carbon-carbon bond. And the transition state here for step 2 is going to be boring. It's just going to be a long bond between, a long forming bond between carbon and the cyanide carbon with a partial negative on the cyanide. This is step 1, this is step 2. Again, you would predict something, an energy diagram kind of like this. Though I guess we could talk about which of these steps, transition state 1 or transition state 2, do you think would be higher in energy? And here's where the idea that breaking bonds is more costly than forming bonds. In transition state 1, we are breaking a bond, so that's why this step is uphill. In transition state 2, we're starting to make a bond. So we would expect this energy difference here to be larger than this energy difference there. It costs more to break a bond than it does to start to form a bond. And so we would predict that this first step would be the slow one. Yeah? Why is it taking energy to start to form the bond here? That's a great question. It probably has to do with the energy required to rearrange the geometry of the molecule. All right, that's enough for today. Catch you guys on Friday.